Swayam Prabha. Digital India. Educated India.
Plus finally the current through R13, that is equal to V3 minus V1 times G13, and this has to be equal to total current contributed by independent current sources flowing into the node, and that is equal to I3. Okay, so basically I have written KCL at the three nodes, and I have followed the convention that I earlier described. All the independent sources on the right hand side and the variables on the left hand side, and all the variables are basically the node voltages with respect to the reference node. Okay, now I understand that this analysis, it is systematic analysis, so there are many steps. Like I said earlier in the course also, please be very systematic and be very careful about the signs when you do these things, especially in the initial parts when you don't yet have much practice. I will stop here and then take any questions. If any of you is not clear about any of these terms, then please ask the question and I'll answer them. Any questions at all? So everything is clear. There are no questions about how I wrote these things, and every term of every equation is clear. Okay, good. So everything is clear to everybody. Now, although I wrote the equations like this, I will rearrange them slightly. Again, remember the variables here are V1, V2 and V3. Okay, the KCL equations are written in terms of the node voltages with respect to the reference node as the primary variables. So when we solve these equations, we will be solving for V1, V2, V3, and from there you can solve for everything else. Okay. So this is one of the equations. This is the other equation. And finally, this is the third equation. Okay. Now I will rearrange these slightly, and what I will do is I will group the variables. That is, I have V1 here, there and there. I don't want to have it like that. So I will write it as V1 times G11 plus G12 plus G13 minus V2 times G12 minus V3 times G13 equals I1. Okay, that is, I grouped all the coefficients of V1 and V2 and V3. Then V2, here I will again write the variables in the same order, minus V1 times G12 plus V2 G12 plus G22 plus G23 minus V3 G23 equals 0, and finally for the last one, minus V1 G13 minus V2 G23 plus V3 G13 plus G23 plus G33 equals I3. Okay, so all I've done is to rearrange the equation so that I will have the variables together. Okay, that is, each variable has all of its coefficients grouped together. I think this is pretty clear, and probably there will be no questions about this. Now, a very common way of writing out these equations, okay, is in the form of a matrix, and this is because it just looks neat. That's the main reason, right? And then on the computer we have methods of solving the matrix, solving the inverse of the matrix, and that's why we write it like that. So now the variables V1, V2, V3, I'll put it into a vector. Okay, and a vector is nothing but in this case a 3×1 matrix or a 3×1 vector. In general, if you have n nodes, you will have n minus 1 independent voltages. So n minus 1 times 1 vector. Okay, and now I will write this whole thing as some matrix times this variable vector equal to the independent source vector. Now what is the matrix? It's nothing but these coefficients which multiply V1, V2 and V3. Okay, so the first element of the first row will be G11 plus G12 plus G13. The second element would be whatever multiplies V2. Okay, you know that when you multiply matrices, you multiply this first element by the first element here, second one by second one, and the third one by third one. So we will have minus G12 minus G13. Similarly for V2, this minus G12 is the coefficient of V1, and G12 plus G22 plus G23 is the coefficient of V2, and finally minus G23 is the coefficient of V3. Okay, and here minus G13 is the coefficient of V1, and minus G23 is the coefficient of V2, and G13 plus G23 plus G33 is the coefficient of V3. Okay, it's exactly the same as what I have here. Each of these rows corresponds to each of these equations. Okay, and this whole thing will be equal to whatever I have on the right hand side. So for the first one, the right hand side is I1, for the second one it is 0, and the third one it is I3. Okay. So this part is called the conductance matrix. Obviously it consists of conductances. And this part is the vector of node voltages. I'll call that V. Okay. And finally this is the vector of independent current sources. Okay, I will call that I. So when we write this equations for the circuit based on Kirchhoff's current laws and express the currents as voltage times conductance, we will get this equation of the form, which is the conductance matrix G times the variable vector V equals the source of independent vectors I. Okay. So conductance matrix times variable vector equals source vector. Now if you want to solve for V, this means that V equals, you know how to do this, you have matrix times vector equals another vector. This is a square matrix. It will be the inverse of this matrix times I. Okay. This is somewhat like if you had scalars, let's say you had A times X equals Y, you would say that X is Y divided by A, or A inverse, which is 1 by A times Y. And now we have it in terms of matrices, so this is the solution. Okay. Now this whole thing, it's basically about setting up the equations correctly. Now, as I said, this is scalable to very large circuits. So whatever the size of circuit you have, you will be able to do it like this. Obviously in exams and in tests and by hand, you will not be solving for anything more than a circuit with 2 nodes or at most 3 nodes, because you will not be calculating inverses of more than 3 by 3 matrix by hand. Okay. But right now the point is to understand how to set this up without any errors and with confidence for any sized circuit. Okay. Any questions on anything that I have done so far? What I have done is to set up the KCL equations at n-1 nodes, and I have chosen the voltage at these n-1 nodes with respect to the reference node as the primary variables. Okay. Okay, it appears that it is pretty clear. So right now I don't want to solve this. I am not going to solve it for any particular circuit, but I just want to focus on the structure of these structure of the matrix here. Okay, let me copy this over. Now the way I have written it is, the first row corresponds to KCL at node 1, and the next is at node 2 and node 3, and I have chosen the same order for the voltages in the vector. Okay, because I can write these in any order, and I can also reorder these and change the order of the entries in the matrix. But the important thing is that I choose to have the KCL equations in some order, n1 first, then n2 and then n3. Then I will also have the voltages in the same order, V1, V2 and V3. Okay, and this is the kind of conductance matrix that I get. So now my question for you is, what do you see about this matrix? What properties do you observe in the matrix as it is written? Okay, I think many of you very easily observed that it is a symmetric matrix. That is, we have minus G12 here, minus G12 there, minus G23, minus G23, and minus G13, minus G13. Okay, so clearly it's a symmetric matrix. Okay. Now let's focus on the diagonal. The diagonal is this, right? What do you observe about the diagonal elements? It is a symmetric matrix. What do you observe about the diagonal elements? For instance, the very first entry of the matrix, right? The element 1 1. What is that? And clearly, I think this also all of you were able to figure out correctly that the diagonal elements are sum of conductances at that node. When I say that node, the matrix entry, this is the element A11. If I call this A matrix, A11 is the sum of conductances at node 1. Similarly, this A22 is the sum of conductances at node 2, and this is at node 3. Okay. Now, what are the off diagonal entries? What is this? Let's say I call this element A12. I think you know the matrix notation. You have A11, A12, A13, and so on. What is this element A12? Yeah, again, I think it's pretty clear. The off diagonal elements are if I take the element Aij, it is the conductance or the negative of the conductance between the node I and j. Okay. So that's how we have. That's why this entry A12 is minus G12. That is the conductance between conductance connected between node 1 and node 2, and it's also why the matrix is symmetric. This is the conductance connected between node 2 and node 1. Obviously, that's the same as the conductance between node 1 and node 2. So that's how we have symmetry. But to get the symmetric structure, please note that the ordering of the node equations and the ordering of the vector has to be exactly the same. Okay. For instance, if I could interchange these two equations, okay, this row will come here and this row will go there, and similarly on the right hand side it will change, but then the symmetry is lost. You will have the symmetric structure only if the ordering of the equations is the same as the ordering of elements in the vector. Okay, is this clear? So now this can be extended to circuits of any size, right? The only restrictions we have so far are that we have only independent current sources and conductances. Okay, we have only independent current sources and conductances in the circuit. With that, we have all these nice properties that we get a symmetric matrix with the diagonal elements being the sum of conductances at that node and off diagonal elements being the conductance between two nodes. Okay, the negative of that. Okay, any questions so far? And to solve for this, you will have to invert the matrix G and multiply the multiply the source vector with the inverse of the matrix G. Okay. So in summary, nodal analysis consists of, first of all, writing KCL at n-1 nodes. First, before this, let's say you choose a reference node. You write the KCL at n-1 nodes in the form of sum of currents flowing out equals independent source currents flowing in. Okay, and also this current is written in terms of node voltages with respect to the reference node. Okay. Now what this will give you, you will get an equation of the type G matrix times V vector equals the source vector. Okay, and solving this will give you the node voltages G inverse times I. Okay. Now we have not yet solved for the complete circuit. Like I said earlier, the complete solution consists of solving for every branch voltage and every branch current. But the hard part is done now. Okay, we have a complicated network and we have found all the node voltages. Okay, now if you want to find all the branch voltages, that's very easy. Okay, for instance, the voltage across R11 is nothing but the voltage between node 1 and node 0. Okay. So let me see. Let me call this, I've already called this V1, that is the voltage between N1 and N0 is V1, N2 and N0 is V2, and N3 and N0 is V3. So the voltage across R11 is V1, R22 is V2, R33 is V3. Okay. Across R12 it is V1 minus V2 in this direction. Across R23 it is V2 minus V3, and across R13 it is V1 minus V3. And also across this current source in this direction it is minus V1, and in this direction it is minus V3. The reason I wrote down all these things is just to show that all the branch voltages come out of some trivial manipulation of the node voltages. Okay. So generally when you say solve for this, we will solve for the node voltages and leave it there. And if there are any other specific question that is questions that are asked, like the branch voltage of a specific branch, you can easily construct it by taking the voltages across that branch, that is taking the difference of two voltages, or maybe in some cases like R11 the node voltage itself is the branch voltage. Okay. And similarly now for branch currents, you have to go to every branch and look at the current voltage relationships. You know the voltage of every branch, so you will be able to tell the current of any branch. Okay. For resistors the current is proportional to the voltage, and for these independent current sources the current is already known, they are independent of the voltages. Okay. So what I want to point out is that after this there are a couple of steps to get all the branch voltages and all the branch currents, but at this point we say the circuit is solved because the rest of the steps are kind of trivial. Okay. Because you just take the difference between some two node voltages to get the branch voltage, and you multiply that by conductance to get the resistor currents. Okay. So we have come to the end of this lecture. In the next one we see that our circuit has some limitations. We have not analyzed a circuit that is universal. We only have current sources and resistors. Obviously we will also have independent voltage sources as well as control sources, that is dependent sources. Okay. So that we will take up in the next class onwards. Now before we leave, a couple of quick questions. So let me first say that to this circuit I will add a current source. Okay. Yet another current source. Let me call it Ix just for simplicity. Now please answer the question, how will this matrix be changed? Okay. Hope you remember what I wrote. Maybe I will copy that over. Let me copy over this whole thing. What I did was to add this current source in blue. Okay. And my question is, I have set up these equations in the matrix form. How will this be changed? Okay. That is, please answer the question in terms of what will change. Is it the, first of all, is it the right hand side that's going to change or the left hand side? Yeah, I think it's pretty clear because we've added an independent current source that has to appear on the right hand side. So the right hand side will change. Okay, this will influence the right hand side. Now how will it change? Okay, which will change? Which of the entries will change? So the right hand side has a vector with 3 elements. So which ones will change? Again, it's pretty clear. This is connected to node 1 and node 3. Obviously, it's only the equations at node 1 and node 3 that will change. Okay. Now, what has happened is that node 2, we have not changed it at all. So, the middle row remains exactly as it is. If you look at node 1, this current source Ix is pointing towards node 1. So, it adds to the current flowing into node 1. So, instead of this I1, it will become, this I1 will become I1 plus Ix. And if you look at this node 3, I3 is flowing in and this Ix is flowing out. So this part will become I3 minus Ix. Okay. And similarly, if I add I2 in this direction, this will be minus I2. Okay. So by now you should have enough confidence to write down this matrix and set it up for any circuit. Like I said, for arbitrarily large circuits, you are not expected to solve it by hand, but solve it on a computer. But you should be able to set up the equation for any size circuits as long as they have only conductances and current sources. Okay. So if you have any questions, I'll answer them. Otherwise, we'll wind up the session and meet on Thursday. Okay, thanks for coming. I'll see you on Thursday. Bye.